We will now consider Lesson 7.5, which is about the methods of heat transfer. If you are new to this channel, please do not forget to subscribe, hit the bell, and do some comments. I post educational videos at least twice a week. Our Lesson 7.5 has the following goals. Goal number 1, to identify and explain the three methods of heat transfer and their applications to everyday lives. Number 2, to identify the methods of heat transfer that take place in a given situation and to solve problems involving the three methods of heat transfer. The methods of heat transfer. Equally as interesting as the effects of heat transfer on a system are the methods by which this occurs. Whenever there is a temperature difference, heat transfer occurs. Heat transfer may occur rapidly, such as through a cooking pan, or slowly, such as through the walls of a picnic ice chest. We can control rates of heat transfer by choosing materials such as thick wool clothing for the winter, controlling air movement such as the use of weather stripping around doors, or by choice of color such as white roof to reflect summer sunlight. So many processes involve heat transfer so that it is hard to imagine a situation where no heat transfer occurs. Yet, every process involving heat transfer takes place by only three methods. Method number 1, conduction. Conduction is the transfer of heat energy from atom to atom by direct physical contact. Conduction occurs in solids only. Dense metals like copper, aluminum, and steel are very good thermal conductors. A thermal insulator is a material that conducts heat poorly. Heat flows very slowly through the plastic so that the temperature of your hand does not rise very much. Examples of conduction in daily lives. There are all kinds of examples of conduction in our everyday lives. The key is to think about whether objects are physically touching. Cup gets colder while hand gets warmer. Ice gets warmer while hand gets colder. In the figure at the left, a saucepan of boiling water being heated by an electric stove is receiving heat energy from the stove by conduction. The molecules in the hot cup of liquid transfer their heat energy to the molecules in the cold spoon. When ironing a piece of clothing, the iron is hot and the heat is transferred to the clothing. Light bulbs give off heat. If you touch a light bulb when it is on, your hand will get burned. The conduction equation. How fast conduction happens depends on several factors. What material the objects are made from, the conductivity, the surface area of the two objects in contact, the difference in temperature between the two objects, and the thickness of the two objects. In equation form, Q dot equals K times A times delta T over D, where Q dot is the rate of heat transfer. It is the amount of heat transferred per second in joules per second or watts. K is the thermal conductivity of the material. A is the surface area in contact in meters squared. Delta T is the change in temperature in degrees Celsius. It is T1 minus T2. In the figure above, T1 is greater than T2 because heat flows in the direction of decreasing temperatures. T1 is the temperature of one object in degrees Celsius. T2 is the temperature of the other object in degrees Celsius. And D is the thickness of the material in meters. Table 7.5.1 are the thermal conductivities of some common substances in joules per second per meter per degrees Celsius. Let us do some examples now. Example number 1. 293 watts is conducted through a section of asbestos insulating material shown in the figure below that measures 0.09 meters squared in cross-sectional area. The thickness is 2.54 centimeters. Compute the temperature difference across the material. Solution. From the formula, Q dot equals Ka delta T divided by D, here we are given the following values. Q dot is 293 watts. The area is 0.09 meters squared. The thickness is 2.54 centimeters or 0.0254 meter. The thermal conductivity for asbestos as found in table 7.5.1 is 0.16 joules per second per meter per degree Celsius. Rearranging to solve for delta T equals Q dot times D divided by K divided by A. Substituting the given values and simplifying, we get the change in temperature equals 516.82 degrees Celsius. Example number 2. A concrete floor measures 9.15 meters by 12.20 meters with a thickness of 10.16 centimeters. The floor has a surface temperature of 21.11 degrees Celsius and the temperature beneath it is 15.56 degrees Celsius. What is the heat transfer rate through the floor? Solution. We will use the formula Q dot equals Ka delta T over D. Here we are given the following values. The area is length times width, 9.15 times 12.20 equals 111.63 meters squared. The thickness D is 10.16 centimeters or 0.1016 meter. The thermal conductivity for concrete as found in table 7.5.1 is 0.84 joules per second per meter per degree Celsius, and the change in temperature is 21.11 minus 15.56 is 5.55 degrees Celsius. Substituting the given values and simplifying, we get the Q dot or the heat transfer rate is 4,878.32 joules per second or 4,878.32 watts. Example number 3. A 10 centimeter thick block of ice with a temperature of 0 degrees Celsius lies on the upper surface of a 2,400 centimeter squared slab of stone. The slab is steam exposed on the lower surface at a temperature of 100 degrees Celsius. Find the heat conductivity of stone if 4,000 grams of ice is melted in 1 hour, given that the latent heat of fusion of ice is 80 calories per gram. Solution. We are given the following values. The thickness D is 10 centimeters. The temperature of ice is 0 degrees Celsius. The temperature at the lower surface is 100 degrees Celsius. So the change in temperature is 100 minus 0 equals 100 degrees Celsius. And the area is 2,400 centimeters squared. The mass of ice is 4,000 grams. The latent heat of fusion of ice is 80 calories per gram. And the time is 1 hour or 3,600 seconds. We are required to find the heat conductivity of stone. First, we calculate the heat needed to melt all of the ice using the formula Q equals M times LF. M is 4,000, LF is 80, so multiplying these two, we have Q equals 320,000 calories. In 1 hour, or which is equivalent to 3,600 seconds, the heat rate is Q dot equals Q over T is 320,000 divided by 3,000 equals 88.89 calories per second. Thus, from the formula, Q dot equals Ka delta T over D, rearranging to solve for K equals Q dot times D over A over delta T, and substituting the values, the value of K is 0.0037 calorie per second per centimeter per degree Celsius. Hence, the thermal conductivity of stone is 0.0037 calorie per second per centimeter per degree Celsius. Example number 4. A metal rod 0.4 meter long and 0.04 meter in diameter has one end at 373 Kelvin and another end at 273 Kelvin. Calculate the total amount of heat conducted in 1 minute. The thermal conductivity of the metal rod is K equals 385 joules per second per meter per degrees Celsius. Here we are given the following values. Our thickness D is the length of the metal rod, which is 0.4 meter. The diameter is 0.04 meter. So from this diameter, we can compute the surface area, which is pi r squared, which is pi times quantity 0.04 over 2. That is now the radius squared. So the area, surface area is 0.001256 meters squared. The incoming temperature is 373 Kelvin. To convert this to degrees Celsius, we subtract 273, so that makes 100 degrees Celsius. And the outgoing temperature is 273. Subtract 273 equals 0 degrees Celsius. The change in temperature now is 100 minus 0, or 100 degrees Celsius. The time is 1 minute or 60 seconds. K is 385 joules per second per meter per degree Celsius. And we are required to find the total amount of heat conducted in 1 minute. So from the formula, Q dot equals K times A times delta T over D, substituting values, 385 times 0.001256 times delta T, which is 100, times 60 seconds in 1 minute, divided by the thickness, which is 0.4. And the value, therefore, of the heat conducted in 1 minute is 7,253.4 joules. Now, let's consider convection heat transfer. Convection is the transfer of heat energy by the movement of the atoms themselves. Convection occurs in liquids and gases only because their molecules can move freely. The molecules of a solid are held closely together. They cannot move freely, therefore convection is not possible in solids. Examples of convection in daily lives: land breeze and sea breeze. Land and sea breezes are the result of convection. On a hot day, the temperature of the land increases more quickly than the sea. It is because the specific heat of land is much smaller as compared to water. The air above land gets hot and rises up. Cold air from the sea begins to move towards the land. It is called sea breeze. At night, the land cools faster than the sea. Therefore, the air above the sea is warmer, rises up, and the cold air from the land begins to move towards the sea. It is called land breeze. Another application is on electric kettles. The heating coil of an electric kettle is always placed at the bottom of the kettle. When power is switched on, the water near the heating coil gets heated up, expands, and becomes less dense. The heated water, therefore, rises while the cooler regions in the upper part of the body of the water descend to replace the heated water. In air conditioners, the rotary fan inside air conditioner forces cold dry air out in the room. The cold air, being dense, sinks while the warm air below, being less dense, rises, and it is drawn into the air conditioner where it is cooled. In this way, the air is recirculated and the temperature of the air falls to the value preset on the thermostat. In radiator, a radiator transfers thermal energy from one medium to another. Despite the name, most radiators use convection instead of thermal radiation to transfer the bulk of their heat. They are mostly used in buildings, automobiles, and electronics. In a room heating system, for example, hot water or sometimes steam is generated in the internal coils. As the water hits the coil, the air next to the radiator warms and rises. Once the heated air rises, cold air can be drawn into and through the radiator from underneath. This airflow generates vertical currents that distribute warm air throughout the room. Another application is in blood circulation. Humans and other mammals employ convection to regulate body temperature. The heart pumps blood throughout the body at an average rate of 5 liters per minute, and the heat produced by the body cells is transferred to air or water flowing over the skin. If skin temperature is lower than that of the surrounding air temperature, the body gains heat by convection and conduction. But if skin temperature is higher, the body loses heat by conduction and convection. In surface tissues, where the rate of blood circulation is higher, heat transfer is mainly convective. The convection equation. Convection is the method of heat transfer through a fluid in the presence of bulk fluid motion. Convection is classified as natural or free and forced convection, depending on how the fluid motion is initiated. In natural convection, any fluid motion is caused by natural means, such as the buoyancy effect, that is, the rise of warmer fluid and the fall of the cooler fluid. Whereas in forced convection, The fluid is forced to flow over a surface or in a tube by external means, such as a pump or fan. Convection heat transfer is complicated since it involves fluid motion as well as heat conduction. The fluid motion enhances heat transfer. The higher the velocity, the higher the heat transfer rate. Thermal convection. Convective heat transfer occurs whenever an object is either hotter or colder than a surrounding fluid. Convection occurs only in a moving liquid or gas, never in a solid. The basic equation for the rate of convection heat transfer is known as Newton's law of cooling, which is given by this equation: Q dot convection equals H times A times delta T, where Q dot convection is the convective heat transfer rate in joules per second or watts. H is the convection heat transfer coefficient in watts per meter squared per Kelvin. A is the surface area of the object being heated or cooled in meter squared. Delta T is the temperature difference in Kelvin. T infinity minus T of the surface temperature, where Ts is T surface temperature of the object in Kelvin, and T infinity is the ball temperature of the surrounding fluid in Kelvin. The algebraic sign of Newton's law of cooling is positive for T sub infinity greater than T sub S, that is heat transfer into the object, and negative when T sub infinity is less than T sub S, that is heat transfer out of the object. The convective heat transfer coefficient H is usually a positive, experimentally determined value. There are two types of convection: natural convection and forced convection. Natural convection is produced by density differentiation of fluid due to temperature differences, example as in hot air rises. Global atmospheric circulation and local weather phenomena, including wind, are due to convective heat transfer. Figure A illustrates natural convection around a hot object. In forced convection, the fluid motion is generated by a source like a pump or a fan. It is one of the main forms of heat transfer used by engineers because large amounts of thermal energy can be transported efficiently. It is used in heating and air conditioning systems, electronics cooling, and in numerous other technologies. Forced convection is used in designing heat exchangers, in which one fluid stream is used to heat or cool another fluid stream. Figure B at the right illustrates a flat plate being cooled by forced convection from a fan. Table 7.5.2 gives us the convection heat transfer coefficient H under various conditions. In 2 units, can be BTU per hour per feet squared degrees Rankine, or in watts per meter squared Kelvin. Let us continue with the examples. Example number 5. A new computer chip with a surface area of 1.00 centimeters squared generates 10.0 watts of heat. Determine the convective heat transfer coefficient needed to keep the temperature of the chip less than 20.0 Kelvin above the environmental temperature. If the chip is to be cooled with air, will it require free or forced convection? Solution. Here we are given the following values. The surface area, 1 centimeter squared. or this is equal to 0.0001 meter squared. The Q dot, which is the heat transfer rate, is negative 10.0 watts. The sign is negative because the chip is losing heat. T infinity minus Ts is negative 20 Kelvin. The surface temperature T sub S is greater than the environmental temperature T sub infinity here. We are required to determine H from the Q dot equals HA delta T and compare it to the values in table 7.5.2. Rearranging the above equation to solve for H is equal to Q dot over A over delta T. Substituting the values, we get H is 5,000 watts per meter squared Kelvin. Table 7.5.2 has this value of H in the forced convection range for liquid and cannot be achieved by air. Now let's go to radiation heat transfer. Radiation is transfer of heat energy through waves. Radiation can travel through space. Examples of radiation heat transfer in everyday lives. Here is a group of examples of radiation in everyday life. The transmission of electromagnetic waves through the microwave oven. The heat emitted by a radiator. Solar ultraviolet radiation, precisely the process that determines the Earth's temperature, and so on and so forth. We have the radio waves, a laser beam. The black body. Radiation heat transfer can be described by reference to the black body. The black body is defined as a body that absorbs all radiation that falls on its surface. Actual black bodies don't exist in nature, though its characteristics are approximated by a hole in a box filled with highly absorptive material. The emission spectrum of such a black body was first fully described by Max Planck. A black body is a hypothetical body that completely absorbs all wavelengths of thermal radiation incident on it. Such bodies do not reflect light and therefore appear black if their temperatures are low enough so as not to be self-luminous. All black bodies heated to a given temperature emit thermal radiation. Characteristics of a perfect black body. A perfect black body absorbs all the radiant heat incident on it. The coefficient of absorption for it is equal to 1. The blackness of such a body is due to the fact that it does not reflect or transmit any part of the heat incident on it. Thus, the coefficient of reflection and coefficient of transmission are 0. The radiation energy per unit time from a black body is proportional to the fourth power of the absolute temperature and can be expressed with Stefan Boltzmann law as Q dot rad equals sigma times T to the fourth times A, where Q dot rad is the radiation heat transfer rate in watts. Sigma is the Stefan Boltzmann constant, which is equal to 5.6703 times 10 to the minus 8 watts per meter squared Kelvin to the fourth. T is the absolute temperature in Kelvin. A is the area of emitting body meter squared. Example number 6. If the surface temperature of the sun is 5,800 Kelvin and we assume that the sun can be regarded as a black body, what is the radiation energy per unit area of the sun? Solution. Modifying the above equation, we get Q dot rad over area equals sigma T to the fourth. And substituting the values, we have 6.42 times 10 to the 7 watts per meter squared. Example number 7. Give and explain a situation where the three methods of heat transfer occur. Answer. In a fireplace, the heat transfer occurs by all three methods: conduction, convection, and radiation. Radiation is responsible for most of the heat transferred into the room. Heat transfer also occurs through conduction into the room, but at a much slower rate. Heat transfer by convection also occurs through cold air entering the room around windows and hot air leaving the room by rising up the chimney. Example number 8. How does a thermos work? Answer. A thermos is a bottle with a double-walled container inside of it. The air between the two walls is sucked out during construction, creating a vacuum. Instead of containing some kind of heating element to keep hot things hot, a thermos is designed to keep hot things hot by not allowing heat to escape. A thermos is built on the principles of all three heat transfer methods. The inner and outer coatings or walls are highly reflective to prevent radiation. They are usually made with silver. A layer of empty space called a vacuum chamber limits conduction and convection, and the lid is a good insulator, usually made of cork, thus preventing conduction. Thanks for watching. Please do not forget to subscribe.